So I'd like to talk today about COVID robust models. So I'm the director of machine learning at RBC, and we have my team basically accounts for about 10% of all the models that are currently in RBC. We have 80 models in production, and we're scaling up to about 120 in a year's time. So obviously, given the current situation, there's lots of decisions to be made on what to build, what to rebuild, especially when COVID's breaking out the models. And I thought I would share today with the group some of the learnings we did, and it might surprise you where we landed on in terms of how do you build models that are robust for COVID. So, as I mentioned, as a COVID-19 situation, a situation involves and modifies behaviors, many pre-COVID models break because and expose limitations of current practices. This is especially true for models that rely on trended behaviors, defunct behaviors, or even many behaviors that are no longer reliable, such as, for example, one of the models that's predicting is whether someone's going to pick up a travel card. Well, no one's traveling right now, so obviously that model's not going to work anymore. And the other thing we found really that's common across all these models is they're all based on non-parametric methods, such as recommended systems, neural networks, tree-based methods. These we found are especially vulnerable and may even mislead with over-optimistic model metrics. Now, I can't show you an actual model from RBC, but I just thought I'll share with you the simulation to show you what I mean. So this is a slide I put together that demonstrates the power of parametric or classical methods, which have been largely forgotten in the recent years, and hype about AI, machine learning. It's all about deep learning, all the sexy new stuff. So the old techniques have kind of fallen back, but they actually provide great value, especially in this evolving time and age. So let me explain the charts you're seeing. So what I did was to show you how stable a parametric model is if built properly. I took the Wisconsin Diagnostic Breast Cancer data set. So on the left-hand side, I trained logistic regression. On the right-hand side was a random forest and XGBoost. I just picked, they all look the same, so I just picked one of them. So logistic regression, as you know, is a distribution-based method. So it's a parametric, whereas the other methods are not. So it's about partitioning variance. So what I did was, once the model was trained, I basically took the test set and I started imputing noise into the test set to see to what extent a random noise in a test set. Basically, I flipped the labels, flip variables, you name it. We know it's not correct, and to see how well that trained model performs. So on the left-hand side, you can see that for the logistic regression, as I put in more and more noise, which is roughly about 20% noise by the time it gets to 50, it starts breaking out. But you can see that it still kind of sticks to the general level of accuracy that it used to be. It will fluctuate, but it tends to hold the course. For the non-parametric methods, and you can see why these will tend to break during COVID, as you introduce more noise in the model, something very interesting thing happens. It starts bifurcating. You can see it goes up and down for each level of noise. And what's happening at the end is, it gets a higher reported accuracy as the error noise increases. So obviously, this is very problematic when you're trying to assess, use your traditional validation techniques to see whether the model's robust or not, because it's obviously not going to give you a correct estimate of what's happening. So what we did was we replaced a random forest of over 500 features with a logistic regression to greater than 20 features. And I guess this also shows you the difference between the current way of doing things, which is put as many features as possible, hope for the best, use ensemble and neural networks to fit everything. So the random forest of over 500 features was built by, the typical computational mindset kind of data scientists. But none of them actually have the skills to build a proper parametric model. So I have a member of my team who was 20 years at the bank, so is really familiar with data and really familiar with parametric modeling because it's a traditional mainstay of the bank. And you can see on the left and right-hand side, so on the left-hand side is the decile chart. You can see that the logistic regression of only 20 features outperforms the random forest of over 500 features across the deciles that matters. And on the right-hand side, you can see that we actually achieve an incremental gain. So this runs counter with, I know many people read, there's tons of these Medium articles about, I did a logistic regression, it didn't work so well, random forest is the best, yay, or XGBoost is the best, yay. So what I want to highlight is that those are kind of one of examples that are not maybe representative of real world data. However, the trouble is parametric is very difficult to do well. And what we found is traditional proprietary software actually outperform open source. Basically, we tried the usual Python R libraries, and they didn't work as well as SAS, because SAS has all these years of really optimizing those kind of their algorithms for the kind of data that the bank is using. So it's very compatible. And also the other issue is most machine learning data scientists do not have the necessary training experience to build a proper parametric model. The reason is the strict distribution assumptions that must be met, which means that not all the times you can build a parametric model. You need to have a very careful independent variable selection. So you have to account for multicollinearity, heterodidacticity, IV order relationship interactions. And third is very important, the equation order actually matters. So there's a lot of manual inspection involved and domain knowledge to figure out which is the permutation that actually works. And to top it off, the next one is it's very easy to overload the equation when you put too many IVs. So unlike, say, a neural network or random forest where you can easily optimize the objective function, it actually doesn't work that way. And I'll show you in the next slide why. And basically, the experience of data and technique is vital. And so I'm just going to use this example, which is the fuel efficiency data set. And the reason why I use this is because this is physics. There's a physical equation we know that underpins it. So it's not like I'm guessing what's happening. So if you look at the first column, so on the left-hand side is all the different variables that's available in the data set. So on the left-hand side, what's full is I basically just train a stupid model that puts all the variables in it and see what happens. And you can see the RMSE and error scores below. And then obviously for the revised one, I said, well, obviously things like model years should not matter into the equation because there's a similar years anyway. So I took that out. And trimmed one gets even more strict that says, well, I should only talk about the reason why I picked displacement over cylinders is because cylinders was 4, 6, 8, and displacement was a lot more variables. So according to typical knowledge of modeling, you would pick the one that has more variance, right? Similar for horsepower versus acceleration. So I picked those. This is a trim model. And you can see that your RMSE for the full is actually less than the revised and the trim. So this is what happens when you overload an equation. Your error shows you as if you've hit the optimal solution, but it's not. And if just for shits and giggles, I put a random variable in the rand to see what happens. And you can see that it really doesn't shift it as much as you think it would. But what actually is, if we actually have the true equation is actually this, so actually only weight and horsepower. And you can see the interesting phenomenon happens in parametric equation, whereby my RMSE is obviously going to be higher than, and my error basically is going to be higher than overloaded model. But you notice that it's actually still lower than the revised trim or random. So this is the kind of the informal elbow kink rule that the old school data scientists use. And just for shits and giggles again, I trained AutoML and it picked absolutely the wrong variables that have nothing to do with efficiency. So this is why building a good parametric model is really quite difficult because it requires quite a bit of domain knowledge to understand which ones you actually need to pick. And this is a straightforward example. Just imagine you have hundreds and thousands of variables. And to make it even more complicated, the algorithm choice can mislead the choice of optimal model. Like I said, so on the top table, you can see that that's a correct one. But if I was to train it using a random forest, the random forest is going to pick the revised or the old ML one, which we know are not the correct ones. So, and this is a good chart. So we recently did a head-to-head test with a leading AI firm in the space. So we were basically trying to predict mortgage discharges, breakages. Basically, you sell your house before your mortgage expires. And so this is a rare event, rare event which is difficult to predict in general, and churn. And so you can see that the power of proper parametric method is not only do you get better performance, it's actually stable over time. And you can see that as it's stable even hitting December 19 to February 2020, which is when COVID is starting to affect all the markets. Whereas if you look at the AI firms, neural network non-parametric method, it starts degrading more than 10% month over month. So all this to say is, when you think of rebuilding robust models, beyond COVID, you should always be cognizant of what the method cannot do. So address the limitations versus what it can do, which is the kind of naive perspective. Revive parametric methods where relevant. Remove embedded and tautological biases, which are quite prevalent in non-parametric models, because a lot of the very strict assumptions in a parametric model are not necessarily, don't have to be held. And also evaluate models on client stratified metrics. And as I've heard in a talk previously about how you want to make sure that the model is predicting correctly for all types of clients, or predicting equally badly for all types of clients, and so it's not overly biased into a specific kind of client group. And of course, finally, you need to prioritize robustness over the accuracy or AUC of your models in order to ensure that your models are also relevant in the post-COVID world and beyond.
Cool. So this one is from Philip. Philip, you have two questions. You said, how useful are shrinkage methods, lasso L1 penalization specifically, for making it easy to fit parametric models? Have you tried norms with exponent less than 1?
Yes. Again, all these regularization methods are just kind of step 1. They're not a final step. So again, because none of these account for the fact that the order equation methods, right? All they do is mix and match different variables together and see what happens. So you're going to drop stuff out, but also you need to be able to control the order it enters into the lasso, because that will also affect what happens. So what you actually need to do is, that's just a useful exploratory stage. You still need to do multiple permutations to figure out, especially if we have no domain knowledge, to figure out what's relevant.
Very good. And Philip is coming at you for another one there. Does SAS have good support for shrinkage methods?
Yes, it has the L1, L2, the usual, and the elastic net. But again, I think it depends on, because it's an enterprise kind of software, it really depends on, the version and the packages that was licensed.